Hi, my name is Kevin Chen, and this is Physics 2212, Lab 4, Bar Magnets. In this lab report, I am going to introduce the purpose and results. I will then review some key physics principles and the experimental procedure. We will then observe and analyze the data before making calculations. We will look at the computational model as well as the assumptions made and experimental errors. Lastly, we will address discussion questions before going into the conclusion. So the purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and to compare the measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields, which were derived from the Biot-Savart law. We also created a computational model to compare with the experimental results. And a quick look into the results, the magnetic dipole moment was calculated to be 1.91 amp meters squared. The experimental magnetic field for the off-axis was measured to have a magnitude of 77.2 microteslas, and the simulated magnetic field for the off-axis was measured to have a magnitude of 35.7 microteslas. Going into the key physics principles, we have the magnetic field of a magnetic dipole, which is defined as the magnetic dipole moment, and it decreases with the inverse cube of distance and is given by the following equation. And deriving this equation allows you to determine the magnetic fields at points both on and off axis relative to the dipole. And we also have the distance dependence formula, which states that the magnitude of a magnetic field from a bar magnet decreases as the distance increases. Going into the experimental procedure, we had two setups which consisted of a phone, a ruler, and a magnet. And we used a magnetometer app on the phone called PHYS, and by aligning the phone so that the x component is 0, the magnetic field of the bar was aligned orthogonal to Earth's magnetic field, so the magnetic field of the bar magnet can be measured separately. And the location of the magnetometer chip was found by sliding the phone across a tape with the perpendicular magnet and marking where the x component was maximized and the y component was minimized. And then the phone was flipped 90 degrees and the process was repeated, except the y component was maximized and the x component was minimized. And so the intersection between the two tapes indicated where the magnetometer sensor location was, and then the distances was measured for the on-axis magnetic field of different strengths of 20, 70, 120, 170, and 220 microteslas. The off-axis magnetic field was measured by finding the on-axis distance where the magnetic field was 100 microtesla, and the distance was applied to the y-axis and the magnetic field at this point was measured. These were the measurements collected from the experiment. The data was linearized and a regression line was created. You can see from the graph that there's a negative correlation, which supports the idea that a greater distance from a magnet decreases the strength of the magnetic field by the magnet. This was my equation and calculations to solve for the magnetic dipole moment, which I calculated it to be 1.91 amp meters squared. We observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and when the magnetometer is close to the magnet, the x component of the magnet field increases. For the computational model, the initial conditions were set for the magnet and the calculated magnetic dipole moment magnitude was plugged in for mu mag. Next, we created a function to calculate the magnetic field due to a dipole. The observation locations were determined for the magnetic field calculations. 2 were on axis and 4 were perpendicular to the axis. 2 arrows were created to represent the magnetic field at the locations that were on axis. 4 arrows were created to represent the magnetic fields perpendicular to the axis at the 4 observation locations. Lastly, the magnetic field for the off-axis measurement was calculated. This was the result from the computational model. The red arrow represents the on-axis measurements and the cyan arrows represent the perpendicular measurements. The magenta arrow represents the off-axis magnetic field. For the results, the simulated magnetic field for the off-axis had a magnitude of 35.7 microteslas, and the experimental magnetic field for the off-axis was measured to be 77.2 microteslas. Going to the assumptions and experimental errors, we assume that the bar magnet behaves as a magnetic dipole, we assume that the magnetic field decreases as distance increases, and that there was no interference from any metal objects, and some errors may be external electronic and magnetic objects which affected the data and the readings from the magnetometer. Another error may be the inconsistent placement of the phone and the sensitivity of the magnetometer readings. What if we hadn't oriented the experiment to compensate for magnetic north and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? So if we had not oriented the experiment to compensate for magnetic north, the data would have been affected because the magnetic field from the Earth contributes to the x and y axis. measurements instead of just the y-axis measurement, and this could lead to inaccuracies in the data. It would also be more difficult to isolate and find an accurate strength and direction of the magnet's field. So what if you were to stick two identical magnets together, end to end, and run the experiment again? How would you expect the measurements to differ? So a stronger magnetic field would be produced because the superimposed magnetic fields would lead to an increased effect of the magnetic dipole moments, so the strength would increase, but the direction would still stay the same. This brings us to the end of lab report 4 on bar magnets. Thank you for watching.